introduce today's speaker, which Andre Linde will do, I have the privilege of announcing the Paul H. Kirkpatrick Award, which the physics department established in honor of Professor Paul Kirkpatrick, who was a member of the physics department for more than 28 years before he retired in 1960. And among other things, Paul Kirkpatrick did a lot of work in X-ray research and is credited with the invention of the X-ray microscope and for pioneering work in scientific holography, in fact. But I think he's most highly regarded in the physics department, or equally regarded for a spirited championship of the importance of furthering excellence in the teaching of physics. And so a vital part of teaching in our department involves graduate students who serve typically as teaching assistants in a number of courses. And so we recognize their excellence with the Paul Kirkpatrick Award. And so today, I'll announce that the two Kirkpatrick Award winners are Chris Overstreet. Chris, are you here? You want to come forward? Chris, in his nomination, was described as an outstanding TA for Physics 170, which is taught by Professor Monica Schleyer-Smith. And the nomination said that Chris was truly exceptional in his continual effort to deepen his understanding of statistical physics, that's the subject of the course, and to then translating that depth of understanding into stellar teaching. So his dedication resulted in glowing evaluations from the students and the instructors alike. And so for that, we're pleased to present you with the Paul Kirkpatrick Award. And there it is, Chris. There's also a monetary award that goes with it that's not in there. Deposited, all that stuff. So you'll be receiving that. Ilya Esterlis. Ilya, are you here? Yes, great. So Ilya is also receiving the Paul Kirkpatrick Award. And he is described as a phenomenal TA in Physics 110, which was taught by Professor Sean Hartnell. And Sean went on to say that Ilya is his first pick for a TA in any course he's teaching. So congratulations. Ilya has been an exceptional and caring, has an exceptionally caring rapport with his students and is always quick to respond to their questions. And he's described as thoroughly deserving of this recognition. And he's TA'd not only for Physics 110, the introductory undergraduate mechanics course, but also in Physics 120, 121, which is a challenging introductory electrodynamics course for undergraduates, and Physics 67 and Physics 41. They're all fairly challenging courses for teaching assistants. And Ilya sets an incredible example of excellence. So thank you for that. Okay, that's all I have to say. Andre.
It's a pleasure to introduce Bruce Macintosh here, because he studies, planets which nobody have seen for quite a long time ago, and suddenly not only we see them, but the interest in the planets like that grows day after day, because we just watch what is happening around. We need some place to run. But the problem is that we need to see these planets, and it's extremely difficult because you have very far planet which does not shine by itself. It's shined by the light emitted by a star nearby. So star you can see, but the planet is extremely difficult. That's what Bruce is working for, and he achieved spectacular successes, as this photo illustrates. You find the planet, and the clarity of him is so thank you.
All right. Thank you for the introduction and the opportunity to talk. And the opportunity to give a colloquium that doesn't involve being on an airplane, which is really a pleasant contrast to the normal lifestyle. I'm going to do sort of a broad survey talk about extrasolar planets, a mix of overview state of the art, since there are a lot of people who aren't in this field, and a little bit of focus in the middle on work by my group. And by my group, I represent a very large number of extraordinarily talented scientists and engineers who've worked on the instruments and the data analysis and the observations that are responsible for the direct imaging that Andre alluded to. But the broad question of extrasolar planets, remains interesting whether you want to flee this one or not, and has been interesting for a long time. Whether there are many worlds or not is a question that was once the province of philosophers, was later something speculative for science fiction, and is now actually something we have answers to. We know, obviously, that extrasolar planets exist. We know roughly how many of them there are, and I'll talk about what we know about that as a function of the planet's size and its orbital separation. But there are also a lot of aspects of the question we don't have an answer to. And in particular, what undoubtedly Albertus was thinking about is not the question of, are there planets like Jupiter out there, but are there planets like Earth? Are there planets that actually are potentially habitable, or that even as we speak, do have life present on them? And that's not a question that we have a particularly good answer to, in spite of all the work that we've done so far. But it is a question that we might start to have answers, or at least upper limits on, over the next couple of decades. So I'll talk a little about the very earliest observations, Doppler shifts, the observations of hot Jupiters, and a little bit about planet formation theory, which is sort of a moving target. Theories of planet formation have not succeeded in keeping up with the observations of extrasolar planets, and they have pretty much failed to make any prediction consistent with the next wave of observations, which, as an observer, I think is a great state for theory to be in. A recurring theme in this talk will be the difference between statistics and detailed individual characterization. We're actually in an era where the count of planets, the number of planets as a function of their size, is pretty well constrained over a lot of planet phase space. But the nature of planets, their composition, even something like their bulk density, is much less well constrained, but is what we're moving into, the era of characterization. And so I'll talk about spectroscopic approaches to characterizing giant planets. In the middle, about the work that the collaboration I'm part of does directly imaging giant planets. And then going back to the broad theme, the real cutting edge on smaller planets is the Kepler mission, its ability to detect transiting Earth-sized planets. What we do and don't know from the Kepler mission. Kepler has discovered the first Earth-like planet about 20 times by now, as every successive headline involves Kepler finds other Earth. It's sort of an inverse cry-wolf problem, of course, because none of those really are Earths, and by the time we really find an Earth, everybody's going to be bored of this. I'll try to say something about the limits of what we do and don't know, and particularly emphasize that every time you see a newspaper article that talks about discovering an Earth-like planet, you should cross out the word like, not if you're reading it on your computer screen, but if you're reading it on paper, and write down the word sized, because that's what we really do know. But we have hints as to the nature of these planetary systems and paths forward into the future. I won't talk about stuff other than planets, asteroid and cometary belts. I won't talk about discovery of planets through gravitational microlensing, and I won't talk about orbits and dynamics of planets, although that's another fascinating window on the properties of extrasolar planets. Well, we'll go back a long way. This is the view of the universe a couple of thousand years ago, an Earth and a bunch of stuff that wasn't the Earth that all went around it. And as we all know, that was a fairly intuitively satisfying but terrible predictive model of the solar system. If you attempt to set up a model in which the Earth is holding still and stuff is going around us, you can't do a good job of predicting where Mars is going to be a month into the future, for example, let alone multiple years into the future. Refinements, fiddly things, epicycles help people to do it, but obviously not in a very satisfying way. And of course, what moved beyond that was the Copernican revolution, but even more, as physicists, the Keplerian revolution, where we have not just a concept, maybe the sun's in the middle, but a set of equations that govern the motion of planets around the sun that in turn let you make predictions. And Kepler's predictions really were astrophysical ones. He could write down where Mars would be 2 months in the future based on his model of the planets going around in elliptical orbits. He could go to his patron Tycho, who had a set of observations, compare those predictions to the observations, and show, by making the 16th century equivalent of Python matplotlib plots that the residuals and his predictions of the positions were relatively small, therefore his model was correct. And that was compelling to scientists, but maybe not compelling to people as a whole in terms of our picture of what the universe looks like. The other step that was involved in the popular revolution for realizing the Earth wasn't the center was looking through a telescope, was actually imaging, not of extrasolar planets, but of exo, in the sense of not the Earth, moons. The moment Galileo looked through his telescope, one of the first things he saw was Jupiter with a few dots next to it. The next night he saw the dots in different position. The night after that he saw the dots in different position. Rapidly he realized he was seeing things orbiting something that was not the Earth. And it's interesting that this visual demonstration is what was sufficiently compelling to be a threat, say, to the established authority. Nobody locked Kepler up for making plots and writing down a bunch of equations. Galileo, looking through the telescope, also because he was a jerk, not just because he had visual implications, but was what captured the popular imagination. At the time they were doing that, of course, the solar system had about 5 planets. For a little while, the solar system had 9 planets. Now we're down to 8 through no fault of the planets. But with a clear distinction that's worth noting. In our solar system, planets, the real planets, sort into 2 distinct kinds. Close to the star, they're small, they're made out of rock. Far away from the star, they're large, they're made out of gas. And when I went to graduate school, I was basically taught that this is what every solar system was going to look like. There's the orbital periods attached onto them. I'm going to show a diagram like this as a recurring theme. I don't know if is there a way to dim the front lights slightly?
Yes.
Too many switches?
Yeah, well, just...
Good.
Is this better? No.
That's less good.
Okay. I mean, you could...
The ratio of slide visibility and napping, I think, is pretty reasonable. So people in the front can nap, people in the back can stay reasonably awake. It'll be good. And I have a not even remotely eye-safe class 4 laser pointer, so napping might be a good strategy. Okay. Planet mass, planet orbital semi-major axis, planets that existed around the time I entered graduate school. And in this diagram, you can see the sorting into 2 broad categories. A giant region of gaseous planets, not shown on this diagram, but a third number we know about them is their density, and those densities were low. And an inner region of small rocky planets. And we were, as I said, taught essentially that this was an inevitable consequence of the planet formation process. The planet formation process starts with the star formation process, which was much more interesting to everybody at the time. Large clouds of interstellar gas condensing to make a protostar in the center. And from conservation of angular momentum and loss of angular momentum in some planes, that cloud flattens into a rotating disk. A rotating disk that will be hot near the protostar and cool further away from the star. Here's kind of a schematic of that. Sitting in it, in this schematic, I didn't put any down here because I got tired of cutting and pasting dots, but imagine they're dots down here, are particles of interstellar quality dust. Dust for astronomers actually means particles on about a micron scale, so they're more like interstellar smoke, but we refer to them as dust for historical reasons. And I've marked 2 different classes of particles. The white particles are composed of volatiles, of stuff like water ice, carbon dioxide ice, carbon monoxide ice. The, I think green, but I'm not sure because I'm colorblind, particles are composed of more refractory materials, silicon, iron, and such like. And you'll notice, of course, that close to the star, there are no white particles because close to the star it gets warm, and ice, whether it's water ice, carbon dioxide, or carbon monoxide ice, sublimates. Far away from the star, there can be both kinds of particles. And you'll also notice white particles are a lot more common because the mixture of elements in our galaxy right now, or in our galaxy back when the solar system formed, carbon and oxygen and of course hydrogen are much more common than silicon and iron and all the stuff you can make refractory materials out of. So we think in the early protosolar nebula that the density of these dust particles was higher, not enormously higher, factor of 2 or 3 higher, in the outer parts of the solar system beyond what we refer to as the snow line, the radius of sublimation for these dust particles. Then, as all these dust particles are orbiting around, initially kind of orbiting at the same velocity of the disk gas, because micron-sized particles don't have any choice but to move with the gas, random motions will cause them to collide. And in that statement, a miracle is sort of buried. It's very hard to numerically model the collision of micron-sized particles that aren't in fact spheres. Very hard to measure the microturbulence that dominates their velocity. And when you do model it, it's surprisingly hard to get them to collide. Collisions don't tend to produce these micron-sized particles sticking to each other. But because planets are observed to be bigger than a micron, it's assumed that they do stick to each other, and that's buried in the early models of planet formation. Those collisions, though, of course, will be much more common the higher the density of particles is. So in the outer parts of solar systems, the collision rates will be higher, and you will build up, somehow, larger scale, meter scale particles on a time scale when you haven't really built meter scale particles on the inside. The meter scale particles will collide and make kilometer scale particles. The kilometer scale particles will collide and make 10 or 100 kilometer particles, until at the end of it you have something maybe 10 times the mass of the Earth, thousands of kilometers across, orbiting in the outer part of the disk. Well, the inner part of the disk still hasn't really got its act together, and maybe it's grown to meter scale, if even that. At that size, it's actually big enough that it clears a gap in the material around it, so it sort of stops accumulating any more material because it's opened a gap in the protoplanetary disk, but still slowly grows, then eventually gets big enough that its Hill sphere, its region of gravitational influence, is bigger than its gap, and it can start sucking material in from the disk itself. It will then rapidly build up an envelope of disk gas material around it, maybe 10 or 100 times the mass of the original core. Just around then, the stuff in the inside has gotten its act together and gotten to kilometer scale material. But by the time the stuff on the inside has gotten to sort of Earth equivalent material, the gas in the disk has dissipated in the classic planet formation model, either accreted onto the star or been blown away by the solar wind as the star switches on. And so you end up with a system like our own, where planets in the outer solar system, largely because they got this head start, are allowed to be giants. Planets in the inner solar system are small stuff made out of rock that we can actually live on. So that's planet formation theory, sort of 1994 style. And what produced a challenge to this theory was very happy when it only had one solar system to respond, because you got a lot of knobs in the theory, and so you can fit a single set of observations easily. It was really, though, when we started to detect extrasolar planets. The first detections, and I'm also not talking about pulsar planets, with apologies to Roger and other people who might want that part of the story. It's a fascinating sub-story, but they're weird. Not the planets, not Roger. The first large-scale detections were done through Doppler shifts, as shown in this animation. Start animation, there we go. Of course, as a planet and a star orbit, they really orbit around the center of mass, as a result of which the star moves towards and away from us in our line of sight, as a result of which the star spectrum shows a Doppler shift that can be detected. In our solar system, that Doppler shift from Jupiter is about 7 meters per second. The state of the art for detecting these Doppler shifts extrasolarly is about 1 meter per second, so we can easily see the signal from planets like this. Though, of course, no one will believe you until you've waited an entire orbital period, so this is a technique that requires patience, which was an issue in early versions of the search. The first successful detections happened before 1995, 1989, and then published in 1995. And already they were kind of a surprise compared to our solar system. By 1999, enough planets had been detected that it was clear that there was a distinct population different than the population of planets in our solar system. They're Jupiter-sized, sometimes a little bit bigger, sometimes a little bit smaller. Clearly, selection effects exist, so lower mass planets with 1999 technology couldn't be seen. Planets out here couldn't be seen because their signal isn't strong enough, but planets were seen in a region where they weren't expected to exist. These planets were referred to as hot Jupiters, unimaginatively because they're the size of Jupiter and they're close to a star, so they're hot. To try and salvage planet formation theory, the first models involved making them the old-fashioned way, making a planet out here at Jupiter-like separations, but then migrating them. That gap that the planets clear will induce a torque on the planet and cause it to lose angular momentum and come inward. In addition, even more so when it starts to stream and accrete material. And so it's actually a very natural consequence of the classic planet formation model that planets should migrate. In fact, migrate so much that it's not completely obvious why this didn't operate on a larger scale in our solar system, or why the hot Jupiter-like planets would even stop migrating and not hit their star. Alternatively, planet formation could happen through a different process. If these protoplanetary disks are sufficiently large and massive, they'll be unstable to gravitational instabilities. As they rotate, they'll build up spiral structure through self-gravity, and that spiral structure, if it exceeds critical densities, will collapse down into planet-sized lumps of gas and dust. In this simulation, it's making about half a dozen lumps like that. going around. The instability also is fairly natural if you have a sufficiently massive and sufficiently cold disk. But all of these are challenging to simulate. The simulation you're watching, you can sort of see the number of times it goes around. If those were Jupiter scale, the number of times it goes around would tell you that the simulation spans about 200 years. The disk is supposed to be about 3 million years old, and in 200 years of simulation, it immediately falls apart and becomes unstable. What that's telling you is you got the initial conditions wrong, that you set it up to be unstable. Greg Laughlin at Santa Cruz, who did a bunch of these computer simulations and analytic simulations as part of his PhD thesis, compared it to simulating the process of a pencil being balanced on its edge and falling over. Naturally, pencils do fall over when you balance them on their point. The question is, why was it balanced on its point in the first place? That was not a question he could answer with his computer simulations. In general, though, you could imagine disks start in a stable configuration and as they change mass or cool down, evolve into the unstable configuration. And then finally, you could also form planets the old-fashioned way in relatively wide orbits and have them gravitationally interact with each other to change their orbits. This three-planet system, and again, it's very artificial because it's becoming unstable on 30 or 40-year timescales, but the mutual interactions of the planets are causing their orbits to change. Orbits are now crossing. That's really bad. One of them gets ejected from the system, carries away a bunch of angular momentum and energy, as a result of which the other two planets have been dumped closer to their star. This, again, almost certainly does happen. There's evidence it happened in our solar system. So planets don't necessarily stay where they formed. And each of these models make different predictions for giant planets. The disk migration generally puts planets on circular orbits, and it mostly migrates them in. They want to be inside the ice line. Multi-planet scattering tends to put planets on crazy elliptical orbits unless something comes along and circularizes them later, and of course requires multiple planets. The instabilities of disks require really massive disks, and so they tend not to make planets. They tend to make brown dwarfs, objects that are maybe 50 times the mass of Jupiter, and would tend to make multi-planet systems. They also make predictions about composition. In the classic disk model, the formation of Jupiter I described, Jupiter has a core of heavy elements, oxygen and carbon, heavy by astronomer standards, as a result of which it doesn't have the same composition of the sun. Jupiter is enhanced in heavy elements compared to the sun. That's a consequence of the fact that it accreted solid material and slowly built itself up. If you just take a lump of disk and collapse it through an instability into a star, you'll basically get a planet with the same composition as the star, with stellar metallicity. And for the physicists in the audience, metals for astronomer means everything that's heavier than helium. So if I use the word metallicity, I'm just referring to every non-primordial heavy element. Modern planet formation has started to blend these and move beyond the simple paradigm. This is not even a 1995 or a 2000 planet formation idea, more like 2008. In particular, although going from micron scale particles to millimeter scale particles is still challenging, millimeter scale particles have interesting physics. Something that's, say, a kilometer across, or let alone 100 kilometers across like the Earth, doesn't care that it's in the middle of a disk made out of gas. It just plows right through the gas. It experiences no interaction with the disk. Something that's a micron is completely coupled to the disk of gas, and so it just stays where it is, moving around with the disk of gas. Something that's a millimeter across experiences gas drag, which causes it to spiral inward when you do all the math correctly. So millimeter scale particles will move inward and also slow down with respect to each other, which makes it easier for them to collide to each other. And as they migrate inward, they can get trapped because they're interacting with a disk. If there are regions where the pressure of the disk changes abruptly, where there's a sharp pressure gradient, the migration can stop and you can get a bunch of these pebble-sized particles piled up. And so modern planet formation sometimes involves not migrating whole planets, but migrating the seeds of planets, the millimeter-sized icy particles, from the outer solar system into the inner solar system. Really what probably happens is sort of all of the above. It's clear planets will interact gravitationally with respect to each other. It's clear planets will experience some migration. And it's fairly clear, everybody likes the pebble stuff, so that pebbles are going on some kind of scale. And it is computationally essentially impossible to simulate this on the million-year timescales that is how long we really think it takes planets to form. So we're stuck with snapshot simulations and analytic scaling. Okay, switching back to observation, one of the clues we have that the original classic process operated in our solar system, as I mentioned, is the metallicity, the abundance of Jupiter. These are Galileo probe values. Jupiter we can cheat. We can actually drop something in it with a mass spectrometer, and so we know the composition of Jupiter's atmosphere pretty well. We don't know the composition of its core, although the Juno mission is going to make some effort towards measuring it. And when we drop the thing into it, we found it's got a little bit less than solar helium, and that's related to what's going on in the interior. We'll ignore neon. But it's enhanced in a bunch of stuff, carbon, nitrogen, and oxygen especially, that the solid ices would have been made out of. And so we have evidence that Jupiter accumulated solid material. We got that evidence by dropping a probe in it, but we could get the same evidence spectroscopically. These are spectra, simulated spectra of Jupiter-like planets with different abundances of methane. Methane is the thing that most carbon gets locked up in, so effectively these are different abundances of carbon. And you can see, unsurprisingly, as you turn the abundance of carbon up, methane absorption features get stronger. Different features saturate, different features change in different ways with respect to the abundance and other parameters. But from observing multiple spectroscopic features, you could predict the carbon abundance of a planet without having to drop something into it. And this was actually done successfully for Jupiter. So if we could get spectra of extrasolar planets, we could say, did they form out of at least partially solid material? The problem is with early Doppler results, you can't get spectra of extrasolar planets. You have press release pictures like this that imply, oh, beautiful planet. This one's actually being has a moon that's being vaporized by its star. With Doppler observations, you don't know that. You just know what its mass is. The next revolution in extrasolar planet studies, though, was studying planets through transits. So another way you can tell a planet's there without seeing it is, of course, if it blocks the light of the star. Planets are opaque, unsurprisingly. If one happens to line up between you and the star, it will absorb light from the star will get a little bit dimmer, transits. The odds of that happening are very low. Jupiter, way out where it is, would have like chance in 1,000 or 10,000 of occulting the sun. The odds go way up if you have a planet close to the star. Conveniently, hot Jupiters close to their star. The odds of a hot Jupiter blocking its sun are about 1 in 100. By the time people knew of 100 hot Jupiters, they found one that blocked its star. If you don't know where planets are and you just want to find this happening, that sounds hard. You have to look at 100,000 stars. But late 20th century, early 21st century, we had really good computers, increasingly good detectors. You could look at 100,000 or 1 million stars to find the 1 in 100 or 1 in 1,000 that line up just right to have this transit happening. And you can do that in part because it's a really easy measurement to make. A Jupiter-sized planet makes a sun-like star drop by 1%. You can measure a 1% brightness change with a telescope in your backyard. And people literally have done this with telescopes in their backyard or teaching telescopes and so on. So by 2004, a moderate number of planets were known to transit. Transiting, nice way to confirm that you have a planet. It gives you its radius as opposed to its mass, so that tells you something about its density. It also was one of the first ways we could get spectra of planets. If you think about a planet blocking the light from its star, some photons, of course, will just hit the planet and get blocked. Some photons will graze their way through the atmosphere and continue on to the Earth. So some fraction of the light will pass through the planet's atmosphere and show the absorption signature of what's spectroscopically present in its atmosphere. A very important caveat, though, is that that only really works for the stratosphere, for the top of the planet's atmosphere, especially if there are clouds present. This toy planet has a layer of clouds. Photons that would probe its lower atmosphere just hit the clouds and don't make it. Photons that take long path lengths through the atmosphere, you lose a lot of light whether you're at an absorption feature or not. But photons that hit the top of the atmosphere will imprint the absorption signature of the composition of the planet. This has now been done for a couple of dozen giant planets. This is a representative one by work by Wakeford, Nicole Lewis, and some other people. It's not a stunning spectra that you'd show in a textbook or anything like that, but it does show spectroscopic features, in this case spectroscopic features associated with water due to absorption in its planet. Models to try and reproduce that actually require a large amount of heavy elements to do that, both to have enough water and then to also make enough clouds to hide the spectroscopic signatures that should have been present from deep in its atmosphere. But from that and sufficient faith in modeling, you can recover this metallicity. And here's a diagram of a bunch of transiting planets that have really good metallicity measurements versus planet mass compared to our solar system. I should say in our solar system there is a trend that the less massive a planet is, the larger fraction of it is made out of heavy elements. Neptune and Uranus are about half heavy elements. Saturn about 10%, Jupiter a few percent. Extrasolar planets, people like saying reproduce that trend. It's probably a slight overstatement. But there's some evidence, certainly, that the extrasolar planets, the hot Jupiter ones, are enhanced in heavy elements and are more enhanced in heavy elements the lower mass they are, consistent with the idea that they formed a core and then accumulated an envelope. So the theory that you form planets the old-fashioned way and then migrate them, at least, is consistent with our picture of other solar systems. We'd really like to know what's going on beyond that. This is a 2007 version of this diagram, more transiting planets, lots of Doppler planets, complete absence of planets out here. not because they don't exist, and not because they don't produce even a strong enough Doppler signal to detect, but just because they hadn't been looking long enough to see them. You only believe a Doppler detection when you see a complete orbit of a planet. Otherwise, you can't solve for things like its period, which is pretty important to getting its mass. The line shows where a planet with a 20-year orbit would be present. In 2007, people hadn't been doing this for 20 years, and so they didn't have sensitivity to see planets where the giant planets in our solar system are. And that's where techniques like our group use for direct imaging of extrasolar planets. That's hard, as Andre alluded to. The analogy I'm required by astronomer law to use is that it's like there's a lighthouse and you're looking for a firefly next to it, which is about right for some of the giant planets we observe. If you wanted to look for a planet like Earth, it's actually like there's a lighthouse and you're looking for a bioluminescent algae next to the lighthouse. More challenging. This is just how challenging that is. This plot is contrast. It's the ratio of star to planet brightness versus angular separation for our solar system if you were looking at it from 10 parsecs away. In our solar system, Mercury is actually really, really bright. It's right next to the sun. Of course it's bright, but extremely close to the sun, making it hard to see. Other planets have a varying range of brightness, fainter as they get further away, brighter as they get bigger. Our ability to do this is limited by two factors. One is just diffraction, the fundamental optical properties of a telescope. You can work to mitigate that, but in the end it sets something we refer to as an inner working angle, the smallest angle at which you can see anything. That angle is proportional to the 1 over the diameter of the telescope. The bigger a telescope, the less diffraction you have, the closer you can see to the star. N might be 1 or 2 or 3 or 4 depending on the design. But of course there's also a limit to how faint a planet you can see, set primarily by things like scattering of light by optical imperfections, residual wavefront error. More precisely, it's proportional to residual wavefront error squared. And so instruments looking for this have a sort of sensitivity inner cutoff and a sensitivity floor, not as binary as I'm showing here. The instruments that do this, by the way, are referred to as coronagraphs, as Phil and others know, because the technology was the first faint thing anybody wanted to see next to a bright thing were not planets, it was the corona of the sun. And so people developed optical techniques to do that. There was a brief move to rename these planetographs when we started looking at planets, but it never really caught on, thankfully, and so we still call them coronagraphs. So if you could build a coronagraph with this performance, you could see Jupiter, yay. We can't build a coronagraph with this performance right now. As of 2008, using the biggest ground-based telescopes in the world and advanced adaptive optics and pretty good coronagraphs, this is kind of our sensitivity floor, long way away from Jupiter. But not hopeless to see a planet, because you can imagine actually and discover planets brighter than Jupiter. The trick was to look at planets when they're young. So basic physics, as I said, we don't understand planet formation. We do understand the initial conditions. There's a big cloud of gas. It's really big, practically infinite. Gravitational potential energy is 0. We understand the final conditions. There's a planet. It is not infinite. It is small. It has a negative gravitational potential energy. Somewhere along the line, energy must have been released. So when planets form, however they form, they're going to be warm. They have to have thermal energy released in the process of their formation. This is a plot of that thermal energy, the luminosity of a planet relative to the sun. So the sun would be up at 10 to the 0. Here is something that's 1,000,000 times fainter than the sun. Versus age. After that gravitational potential energy is released, the planet just sits there cooling down. 4 planets of a variety of masses, from 15 Jupiter masses to 1 Jupiter mass to Saturn mass. And if you caught, at say 10 million years of age, a planet that's the mass of Jupiter, it would only be 10 to the minus 6 fainter than its star, not 10 to the minus 9 like Jupiter is. Exactly how bright it is, of course, depends on what wavelength you're looking at, details of the spectra of the planet, but roughly speaking, that's what the planets would do. And in fact, here's some models of that. These are planets that are all 30 million years old. This one is 8 Jupiter masses, this one is 5 Jupiter masses, this one is 2 Jupiter masses. I've arbitrarily put them at particular separations, but because these planets are radiating heat, their brightness is independent of how far away from their star, and their brightness was within the reach of the technology we had in 2008. And as many of you know, in 2008 that actually worked, and we produced images of an extrasolar planetary system, HRID 799. In the center is the star blocked by the coronagraph. A huge amount of image processing has happened, and so all these lumps you're seeing are light that wasn't quite blocked by the coronagraph, scattered by things like polishing errors on the telescope mirror, partially but not perfectly removed by image processing, but the dots are planets. The star is about 1.5 solar masses. The planets are about 1,000 degrees Kelvin, 5 to 7 times the mass of Jupiter, radiating away happily in the infrared. This is a 4 micron infrared image. The outermost planet is a little bit fainter. It's probably about 900 Kelvin, 3 to 5 times the mass of Jupiter. But these are real planets. This is actual light you're seeing from an extrasolar planetary system. I could gratuitously compare it to our own solar system, as one does. It has 4 giant planets. Our solar system has 4 giant planets. Obviously, it's identical, case closed. Not quite, as these planets are much more massive than our solar system. Like I said, 7 times, maybe 3 to 5 times. They're bigger than our solar system. They're orbiting at scales of 20 to 80 AU, where our solar system is all within 10 to 30. On the other hand, the architecture is like our solar system. Our solar system has a belt of asteroids and a belt of comets. There's indirect evidence that this solar system has an inner belt of asteroids and an outer belt of comets. And planets that are out at sort of 40 AU from Kepler's laws are going to take a very long time to orbit. But we can measure the positions very precisely, and we've been watching these guys for a long time. There we go. A collaborator of mine, Jason Wang, put together this beautiful movie. These are real Keck adaptive optic images spanning approximately 10 years of observation and really watching the planets orbit. They're obeying Kepler's laws. This one's going fast like Kepler said it would. This one's going slow like Kepler said it would. Their shape, as you can obviously tell by doing a 3-dimensional Markov chain Monte Carlo in your head, is consistent with an elliptical orbit. It's not a surprise that they obey Kepler's laws. Of course, that's basic physics. But the fact that we can actually see Kepler's laws from outside for real, not in a simulation, is one of the most awesome things I've seen in my professional astronomer career. And it's just so cool to watch. This one, the fastest one here, has a period of about 40 years. It is a life goal for me to see it complete its orbit, so I'm trying to exercise, eat better, and things like that. I'm also trying to discover planets in a 12-year orbit just in case. The current estimate for the inclination of the orbits is about 30 degrees. And the Markov chain fitting is inconsistent right now on whether they're all orbiting in the same plane or not, however. My bias is that they all are, and that would get into the dynamics and stability stuff I'm not going to talk about. But it's slightly inconsistent. There's some possibility that they're tilted with respect to each other by about 10 degrees, which would be weird. But it's pretty clear it's inclined about 30 degrees. The asteroid belts I mentioned are at about 30 degrees too. So pretty nice. Next slide. There we go. If we can see them, we can get spectra. So this is just one representative case. These are low-resolution infrared spectra of the outermost planet over a broad wavelength range in the near infrared. What you're seeing, there's an absorption feature here. There's actually no spectra here, and that's because on the Earth, water vapor absorbs infrared light at those wavelengths, so we can't really see the planet particularly well. Water vapor is also present in the planet's atmosphere. The absorption here, and to some extent here, is from water vapor in the planet's atmosphere. At much higher temperatures than the Earth, it absorbs over a broader range. There's also some absorption from molecular hydrogen. Again, an interesting side note on molecular physics that I don't really have time to go to. There was supposed to be methane around planets this cold, and there wasn't in this one, which is a surprise, and I'll talk about that in a little bit. There was clearly carbon monoxide. This is the break where carbon monoxide starts to absorb at 2.3 microns. The continuum actually comes from hot, thick clouds of liquid metal in the planet's interior. So we can characterize these planets, say something about their chemistry and their vertical atmosphere structure. Here's kind of what planets should have looked like, and or brown dwarfs and stars. Stars, the coolest stars, have some solid material in them, clouds of extremely refractory stuff like titanium oxide, and basically radiate like black bodies. Somewhat cooler objects, brown dwarf-like objects, have clouds of silicates and liquid metal, also opaque, radiate like black bodies, but up through this cooler atmosphere of the star. We go from hot here down to cool, and so the absorption features of things like carbon monoxide are printed on them. Planets at these temperatures, the cloud level is supposed to be deep enough that we would see absorption not just from carbon monoxide, but as I mentioned, from methane. We didn't, and we think that's evidence that the planet's atmosphere is circulating, that the clouds and carbon monoxide are pulled up while the methane is pushed down into the planet's interior and destroyed. So we can reconstruct not just, well, good news, bad news. We can reconstruct something about the planet's chemistry and atmospheric circulation. The bad news is it actually makes it hard to determine things like the absolute carbon abundance or the absolute oxygen abundance, because it's degenerate with some of these circulation parameters. This has been done by now for about half a dozen planetary systems. I'm realizing I have way too much material in this talk, not surprising, but we'll try to cover a few more, at least results of our group. Complications on this. Here's a plot again. These colored lines are similar to the non-colored one I showed of luminosity relative to the sun, a bunch of different planet masses versus age. You can see them cooling down. As I said, we don't understand planet formation. I kind of said, oh, we think we understand the initial conditions, big diffuse cloud of gas, turn it into a planet. That's only really a valid way to think about it if the planet turns into a planet adiabatically, if it retains all of its energy and entropy in formation. Almost certainly for Jupiter, for example, that didn't happen. Jupiter did not waft down infinitesimally from a giant cloud of gas. Jupiter sucked half of its mass out from the disk surrounding it, almost certainly through a shock, where a lot of energy and entropy got dissipated. And so it's possible planets form colder than the idealized picture. And that's what these sets of lines represent. They're referred to as cold star planets, although they still have temperatures of 1,000 Kelvin, because they formed through accretion of material through a shock, the way we think Jupiter formed. If that happened, they're much less luminous at early ages, which would have been bad news for detecting them. In fact, most of the self-luminous planets we've seen, the young planets, aren't on those curves. They appear to have formed maybe through a different process that let them retain their entropy. And the global instability, the case where the whole disk collapses down to form a planet, would actually be close enough to adiabatic that it wouldn't be a bad description of the planets. But that's one reason you might like to see planets that are fainter than these, especially close to the star. And so from the first generation AO systems, we tried to build next generation instruments that could operate more at the 10 to the minus 6 level that could see planets for a variety of initial conditions. The particular example I was involved in is the Gemini Planet Imager. Big bulky thing, it's about 1 meter on a side. It was built by Lawrence Livermore, where I was before I came to Stanford, who built the adaptive optics system. It has coronagraph diffraction blocking masks from the American Museum of Natural History, an infrared wavefront sensor that JPL built that sort of works, an infrared spectrograph that UCLA built that lets us not just make images of planets, but their spectra, and a big mechanical structure that holds the whole thing together, as well as, of course, a lot of complicated software to make the whole thing hold together. It's deployed on the Gemini South telescope in Chile. There's Gemini South. There's GPI bolted to the back of the telescope. There, from one of our commissioning runs, is a chunk of the large team, also giving you a sense of the scale of the instrument, about 2,000 kilograms of stuff on the back. From our first light, here's an image of an extrasolar planet. There's a couple of complicated features in this image. This was a planet that was known to exist before we observed it. Here, the star has been blocked by these diffraction controlling masks. They aren't perfect, so there's glints of the star, residual light diffracting off the edge of it, sort of like Poisson's spot or the spot of Arago, depending on which side of that argument you're on. Diffraction control is never perfect. These 4 dots are not 4 planets in a perfect square. They're actually diffracted copies of the star that are there on purpose. We want to know when we find a planet, there's the planet, how far away it is from the star. Star got blocked by the mask, so how do I know where the star is? Well, I put a diffraction grating in to make 4 copies of the star. From optical physics, the star will have to be the intersection of the positions of those 4 copies of the star. But that one, real planet. For comparison, here's an image taken with a previous generation instrument in 2010. Planets visible, but not extremely visible. And particularly since that was 3,900 seconds of observation, and this was 60 seconds of observation. So GPI was substantially more powerful, like it was supposed to be, than its predecessor. If we actually spend half an hour and do fancy image processing, the sensitivity is much, much better. We've been using this to carry out a large-scale survey for extrasolar planets. We're looking at about 600 nearby young stars. 900 hours of telescope time. It was supposed to take 3 years. Weather in Chile has been terrible, so we're entering the 4th year of this project. It will probably spill over to 5 if we're lucky. The goal is to detect and characterize large populations of young planets, study the circumstellar disks I'm not talking about. Models said we would find 10 to 50 planets. Spoilers, we haven't found anything close to 50. I'll talk about the implications of that. Originally, we used to fly down to Chile. Now we actually operate the telescope from the Physics and Astrophysics building. There's a remote ops facility down on the first floor. You can bring your dog if necessary, comforting if it's raining all the time, and then observe it over multi-headed computers and watching people in the distance. In fact, almost all the analysis by this point is automated. We have a very sophisticated data pipeline that evolved rather than being designed as smart graduate students and postdocs added features to it. For example, we use Dropbox for archiving data, which is never something you would choose to do on purpose, but Dropbox gave us a couple of 100 terabytes for free, so we're using it. So data gets processed essentially in real time. About 20 minutes after you start an observation, you end up with a complete combined set of data in which signals of a planet or a protoplanetary disk disk are actually visible. The software posts them to the group Slack chat in real time where you argue about which dots are real and which dots are not real. Meanwhile, every property of the observation and properties of the observatory go into a database. We have a researcher here, Melissa Tallis, for example, who's looking at things like whether the temperature of the observatory dome degrades the performance of the instrument due to convection coming off the primary mirror. So we're very happy with our data architecture. Our first discovery of a planet. GPI Data is a little bit complicated because our instrument is not an imager but an imaging spectrograph. So what we actually get is for every pixel in the field of view a spectrum that the sophisticated data pipeline reduces and turns into a reduced spectrum. This is stepping from short to long wavelengths, and you can see at this location something that comes and goes but gets very bright as a function of wavelength. It does that because it's a real signal from a planet, one with strong absorption from methane. These are individual features from methane and the thermal emission from the hot clouds. It's called 51 Eridani b. It's about 20 million years old. I won't talk about its chemistry modeling in detail, but it probably has clouds of salt and sulfides in its upper atmosphere, but models are still somewhat unsatisfying in terms of perfectly reproducing the spectrum. It also probably is partially cloudy. This is a thermal image of Jupiter. At thermal wavelengths in Jupiter, in some places you see very bright because you see deep into the hot interior of Jupiter. Other places Jupiter is cold at infrared wavelengths. Our planets are probably doing the same thing. And its luminosity is consistent with the idea that it is actually on this cold Jupiter-like formation track. Its metallicity is not as well constrained, but is, because these are high-mass planets, is sort of consistent with the solar system-like excursion. We've detected about 6 planets and 4 brown dwarfs with the survey so far. The question we want to answer is how common are these? How many planets are present in the outer parts of solar systems in this sort of classical giant region, inaccessible to Doppler but somewhat accessible to us? And when area was in a circular orbit like this, I could see it whenever I looked at the system. It would always be visible. If it was in a circular orbit that's inclined, some of the time it would get too close to the starlight blocking mass, get lost in the scattered light in between, and it wouldn't be detectable unless it was very bright. If it was in an elliptical orbit, even more of the time, some of the time it would be undetectable, but it would spend most of its time out here at the long end of its elliptical orbit, so its probability of detecting would be complicated. Complicated, but easy to model. So Eric does calculations of the completeness, basically the detection probability for any given star as a function of planet mass and planet orbital semi-major axis, marginalizing over the stuff we don't know. For example, the inclinations of planets, almost certainly random. There's no reason they should point towards or away from the Earth. The orbital phase of planets, almost certainly random. There's no reason they should be close to the Earth on Tuesday or far away. The eccentricities, the ellipticities of the orbit, almost certainly satisfy some distribution that we don't know, and so we marginalize over various assumptions about that distribution of eccentricity. Turns out not to be extremely sensitive to that. So you can calculate this number from 0 to 1. Basically, if there was a planet that was 3 Jupiter masses at 30 AU, according to this, I would have about a 75% chance of detecting it if I looked at the star. 25% of the time it would be too close and be invisible. The rest of the time it would be detectable. If it's really, really bright, like 10 Jupiter masses, I can see it all the time. If it's really faint, like 1 Jupiter mass, odds are I wouldn't see it very often. So Eric calculates that for every star in the survey, and we can add them together as the survey goes through the 400-odd stars that we've observed so far, and we can put on the dots for the detectable planets that we've actually seen. A couple of brown dwarfs that were detected, planet, 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 and then we observed systems that had known planets, but we didn't cheat. We didn't observe them out of order. Our targets are picked by a fully automated process. At one point, that fully automated process says you're allowed to observe the 4-planet system that I showed, so I'm allowed to include it in my statistics, honestly. By the end of the survey, here's the sort of 6 planets that GPI's seen and 4 brown dwarfs. Here's the same figure. It has some interesting implications. This is the low-mass 51 Erie planet, the one that might have formed through core accretion. There's not many stars we could see it around. We could only see it because conditions were very good, which pretty much never happens. It turns out Serapis, terrible site for telescopes. LSST people, too late for you, I know, but you're not going to be happy. But once in a while, the seeing was good. So there's about 16 stars where we could see a relatively low-mass planet. On the other hand, these high-mass planets we could see around almost any star in our survey, as a result of which you can infer that these must be more common than this. But you might want to infer it more quantitatively. What you could do is you could take a model of the occurrence rate of planets, ground it in observation, and then compare it to your survey sensitivity. So this is a plot of the number of planets per star from Doppler surveys, where they've measured, as I mentioned earlier, I would just say 3 astronomical units, masses 1 to 10 Jupiter masses. What's plotted is actually a numerical fit to the number of known Doppler planets, a power law in mass and semi-major axis. It predicts, for example, that there should be about 0.014 planets per star from 1 to 3 AU from 1 to 3 Jupiter masses. Interestingly, implying that planets like Jupiter that we have in our solar system are relatively rare, at least close to the star. The total number of Jupiter-like planets close to the star, if I integrate it all the way into the star, is maybe on the order of 10%. I could take that distribution, I could extrapolate it out into GPI territory, where Doppler people didn't measure it. Obviously, extrapolation is insane, particularly with power laws. But this power law isn't rising extremely fast, and so it makes some prediction that there would be more planets out of 10 AU than there would have 1 AU. This isn't based on a formation model, it's purely an empirical fit to data. So this is the number of planets that would occur in each of these boxes. If I want to figure out how many planets GPI would see around a single star, I would take the number of planets that would occur around each of these boxes, multiply it by the percent chance I have of seeing a planet. I get the probability that I'd see a planet in that box observing a single star. If I want to do it for the whole survey, I take that sum of the probabilities of detecting the planets across the whole survey, the quantity I showed before, essentially how many stars around which you could see a planet, say, between 3 and 10 Jupiter masses, 10 to 30 AU, multiply it by the fact that from the Doppler surveys extrapolated, there should be about 0.025 planets per star in that box, and I can get a prediction, assuming the Doppler distribution of planets continues to be true, for how many planets GPI would see. That prediction are the numbers plotted in that box. If the distribution of planets continues smoothly from the kind of 3 AU scale where it's measured out to our 30 or 100 AU scales, we get about 2 planets here, kind of got 2. We get about 3 here, kind of got 3. We get actually fewer than 1, got 1, fewer than 1 here. The numbers are basically consistent with the idea that planets on the scale we probe are similar to the planets on the Doppler scale. About 0.25 giant planets per star over the whole range of separations. And interestingly, there's no evidence of a sharp increase as you cross that snow line, that magic place where we think Jupiter formed. With the important caveat, we could hide a lot of low-mass planets from GPI. We're terrible at seeing low-mass planets. So maybe planets at large separations, you only make 1 Jupiter mass planet, not 10 Jupiter mass planets. We couldn't really tell the difference. More formally, we do Markov chain Monte Carlo modeling for different model planet distributions and produce constraints on the properties of the power law, but I'm not going to talk about that here, actually. But a second interesting result of the GPI data, here's our 6 planets. Every one of these 6 planets, it turns out the star they orbit is bigger than the sun. It's about 1.5 solar masses. It's not easier to see planets around stars that are high mass. Here's the sensitivity plot for all of the low mass stars in the survey, all of the high mass stars in the survey. Even though we don't have that many high mass stars, they're bright, it's hard to see planets, it's where we find all the planets. And so the observations are consistent with the idea that these giant wide orbit planets are actually very rare around stars like the sun. We got pretty lucky to have Jupiter, and very common around high mass stars, maybe indicating different planet formation processes. These are posterior distributions of the frequency of giant planets per star. Around high mass stars, the posterior wants to be about 20%. Around low mass stars, it's 0% because we've seen nothing, with 1 sigma error bars that sort of say the distributions are different at about the 3 sigma level. Implications of that: giant planets are not very common around solar-type stars. They're more common around high mass stars. We know that planet-forming disks are more common around high mass stars, so maybe planet formation just follows a different path around high mass stars than it does around low mass stars. Okay. But we haven't published this yet, so the planet formation theorists don't have a major explanation for it. I don't have a lot of time to talk about other results in the future, so I'm just going to go through a couple of things very quickly. Getting back to Earth-like planets, of course, the dominant way of discovering Earth-like planets so far has been the Kepler mission, a huge field of view camera looking at a single piece of the sky for transiting exoplanets. This is the 2018 version of that exoplanet landscape, and all of these little green dots, I think they're green, are discoveries made with Kepler, a vast sea of planets at low masses and close to the parent star. Many of them in multi-planet systems, and that's again a dynamics topic I don't have time to talk about. Here's an animation of every Kepler multi-planet system compared to our solar system. One of the things that's interesting is how dense these are. Kepler has found hundreds of solar systems much more densely packed with massive planets, 2 to 3 times or 10 times the mass of the Earth, very close to each other, right on the edge of dynamical instability, and very different than our solar system. What we'd really like to know, though, is how many Earths are there out there? Kepler was designed to be able to answer that question, to be able to see planets in 180 orbits that were 1 Earth radius. It didn't, partially because in budget cutting, it was originally going to be a 5-year mission. They were somewhat over budget. They said, let's call it a 4-year mission. That will save money. Of course, NASA will extend the mission because it'll be successful, so you'll get that money back. Turns out when the warranty on your gyroscope says breaks after 4 years, they break after 4 years. And so Kepler was not able to conclude its core mission surveying planets for 5 years. In addition, stars turn out to be harder to look at than we thought. Of course, a sunspot could look like a transiting planet as it orbits across a star's disk. Stars have more sunspots than the Kepler models thought they did. And so they couldn't quite see what was going on in Earth-like planets. They have to extrapolate into this region to say how common Earth-like planets are. Now, here's the planets detected by Kepler again. We'll skip forward a few slides. The best estimates for that right now, well, there isn't a best estimate. These are different groups' estimates of essentially the number of Earth-like planets in the habitable zone per star versus probability. There's a consensus value around 0.4 Earth-like planets per star, but you can find groups who say there's 3 per star, and you can find groups that say there's 0.1 per star. Depends a lot on assumptions about false positive rates and how aggressively you extrapolate. I don't think I'll go into that, but there's a group led by Russ Bellicott at NASA Ames. He would say that his favorite value is about 0.6 Earth-like planets per star. I am a massive pessimist. I think the favorite value is 0.1, particularly because Kepler only tells you the radius of the star. This is a non-Kepler found, a very famous transiting system called TRAPPIST-1. It has 7 transiting planets. Amazing and awesome. We don't know that they look like that. We just know how big they are. We try to infer something about their composition. There are a handful for which you can measure the mass of the planet because you can get both a Doppler and a transit detection. Here's planet radius versus planet mass for a bunch of known systems. These are curves given by equation of state, the way a planet made out of iron, rock, or hydrogen would behave, with the behavior that they start to get smaller as they get to very high masses. Lots of them look like they're made out of hydrogen. Many of them are bigger than they should be made out of hydrogen. That's because the hot Jupiters get puffed up by their parent star. Down in the low mass region, there are planets known that are sitting on the trajectory for equations of state that have Earth-like compositions. A lot of them, though, are lighter than Earth-like compositions, indicating that they're not really so much super Earth-sized planets as they are mini Neptunes with significant amounts of water or hydrogen envelopes. There's tentative evidence that there's a change in that state around 1.6 Earth radii. This is work by Lauren Weiss, who was a brilliant graduate student at Berkeley, showing the planet density versus radius, that the lowest radius planets have high densities, larger radii planets have low densities, so maybe there is a distinct population of Earth-like planets below about 1.5 Earth radii, Neptune-like above about 1.5 Earth radii, but we really don't know. Let's give a bunch of modern statistics and observations of planets. I should say that when getting spectra of these planets right now is very hard, and when we do, they're really boring. These are the closest things to spectra we have of Earth-like planets from the Hubble Space Telescope result that actually came out this week. They're basically flat. That tells you they probably don't have huge, puffy, Jupiter-like atmospheres, but doesn't tell you whether they have an Earth-like atmosphere or a carbon dioxide atmosphere or no atmosphere at all. What do we know? We know that Kepler systems are very different than our own. Lots of planets bigger than Earth and smaller than Neptune, dynamically packed together. Small planets are very common, including planets that are sort of twice the radius of the Earth, nothing like our solar system. Close to the star, planets do tend to be rocky, but it could be that they had atmospheres that got blown off by the star, and they used to have giant hydrogen envelopes. Really, I think, honestly, we don't know. People can say that Earth-sized planets are common, but our solar system is so different than what Kepler saw that inferring from our solar system that anything that's 1 Earth radius is going to be habitable, dangerous bet to take. I'll just say a little about the future, going through a couple of slides. Kepler, to find its transiting planets, had to look at 100,000 stars. It did that by being a pretty big telescope, 1.5 meters, with a pretty large field of view. And so its 100,000 stars went out to kind of a kiloparsec scale on the galaxy. That's how big a cone you have to search to get 100,000 stars. Downside, when you find a planet, it is hundreds of parsecs or a kiloparsec away because you observed a big chunk of the galaxy.
What you really want to do is look at 100,000 stars over the whole sky. If you look over the whole sky, there's 100,000 stars pretty close to the Earth, as long as you don't limit yourself to staring in one direction. The next most important exoplanet mission will be something called Tess, the Transiting Exoplanet Survey Satellite, and it will do that. It's not even a telescope. It's like 4 giant fisheye lens SLR cameras glued to the front of the spacecraft, not quite, but close. Each camera has a 20 by 20 degree field of view. The 4 of them will survey an enormous chunk of the sky at a single time. It will stare at each chunk of these skies for 2 months and move to the next chunk of the sky. By the end of its 3-year mission, it will be sensitive to transiting planets around every bright star in the sky. And so if it gets lucky and finds an Earth-like planet, it will be around a star that is bright enough to meaningfully get spectral characterization of. Particularly in combination with the James Webb Space Telescope, the other big thing in astronomy, wasn't designed to do this. No one even had invented transiting planets when JWST was designed, but we think it will be capable of doing that. And the last 2 things, and I apologize for especially at this time of day for keeping people slightly late, but there are 2 more things in the future I want to talk about. I want to switch back to direct imaging. So we want to directly image. For Tess and JWST to see an Earth-like planet, there's 2 limitations. One is, because it only looks for 60 days, it can only see planets in short orbital periods. For those to be habitable, they have to be close to their star, which means a low-mass star. So Kepler Tess is really about low-mass M stars. And it's got to get lucky. Even with an M star, the odds that a transit will happen around a star close to the sun, not great. What we really want to do is go back to imaging, being able to see the planets directly, irrespective of how their orbits are oriented. You want to push these inner working angles in and push this contrast floor down. A sort of 4 to 8 meter space telescope with picometer stable primary telescope mirrors, which is hard, would have sensitivities like this that would let you get into the Earth regime. Telescopes like that are on the table. W1st is not going to be it. That if I'd given this talk 4 or 5 months ago, I would talk about how cool W1st would be for planet imaging. Its planet imaging capabilities have been essentially descope. Let me see. That approach, that limitation of seeing planets with space-based telescopes, the requirement, for example, that your telescope mirror be stable at the picometer level, comes from scattering light inside the telescope. That's hard to do. We may not be able to build telescopes that good. The other approach, if you want to see something bright close to something faint, like say you want to see a bird flying close to the sun, what do? You do this. You hold up your hand, right? You do not deploy adaptive optics inside your eyeball, little coronagraph masks. You hold up something big and opaque, far enough away from your eye that it blocks the star, the sun in this case, and does not block the little bright thing you want to see, like the bird. So you could do the same thing for extrasolar planets. You could hold up a giant hand near your eyeball, blocking the light from a star, while the light from a planet peeks around the edge of that eyeball and becomes visible. Probably don't want to do it with giant hands, of course. You want to do it with something we refer to as a star shade. The exact shape of this star shade is complicated. It's set by diffraction. Something doesn't, opaque objects don't cast perfectly dark shadows, of course, because light diffracts. You shape the star shade in a way that channels the diffraction and makes the shadow extra dark. When you do that, the star shade has to be about 30 meters across, about 25,000 kilometers away from the telescope. From a physics standpoint, it's beautiful. It's sort of a nice graduate optics problem to write down exactly how dark that shadow is. There's nothing that can go wrong, physics speaking. Engineering, a little bit harder. For example, the shadow it casts is about 5 meters across. Your telescope is, say, 3 or 4 meters across. Got to keep the telescope positioned relative to the spacecraft to within about 1 meter. When you get bored of looking at this star, you've got to move the pair so that they look at another star. That takes a couple of weeks and uses up some fuel, but aeronautical and astronautical engineers know how to do that. The telescope is really simple. Could work over almost any range of wavelengths. And you can do this with any telescope out there. You could, for example, take the W1st cosmology telescope and add one of these star shades onto it in later life, or you could build a dedicated telescope with a big star shade in the sort of 2035 scale. You might want to test it before you fly something like this at a $1 billion scale. Simone D'Amico, a aeronautics astronautics professor here, has worked out a beautiful concept for a subscale version. So one of the many issues with this, have to hold formation 30,000 kilometers apart. Can't do that in low Earth orbit, because low Earth orbit is not 30,000 kilometers away. You have to get this away from the Earth, either completely in independent solar orbit or in the Earth-Sun L2. That's expensive to do for big stuff, although we just flew a car away from the Earth. It's not as expensive as I thought. But Simone came up with an approach for testing it in low Earth orbit. You have a star shade and a telescope eccentric orbits. When they're out here at the far end of their eccentric orbit, they're hardly moving. And so they maintain formation with respect to each other, even in Earth orbit, for about an hour or so. Then they get too close to the Earth, the formation falls apart. You do a thruster firing down here, that'll line them up so that on the next pass they're lined up again. Get another hour or so of observation. It uses only, that should say centimeters per second. It uses tiny amounts of fuel for every cycle. You could fly a sort of 30-centimeter version together with a 2-meter class star shade on a kind of large CubeSat budget. But beyond that, to really get down to the Earth, we're going to need next-generation missions. The ones that are being studied right now by the astronomical community range from kind of 4 to 5 meter telescopes, maybe with a star shade called HABEX, to this giant Star Destroyer thing, the large UV optical IR telescope, which would be a 16-meter class Super James Webb Space Telescope. The 2020 Decadal Survey gets to consider them. And the last way you could do this, though, these are planets in the habitable zone of the star 5 parsecs away, all of them the size of the Earth. You'll notice they're all different brightnesses, and that's because if you're in the habitable zone of a small star, you've got to be close to the star. Close to the star itself is intrinsically faint, means that the planet is brighter relative to the star. So the lower mass the star is, the easier it is to see the planet in terms of contrast, except that it gets really, really, really close to the star. And the big telescopes, even in space, even the insane 16-meter Star Destroyer, can't work so close to its star that it can see a planet orbiting around the moderately distant, very low-mass stars. On the other hand, this is an actual population of stars in the solar neighborhood, nearby low-mass stars, sun-like stars. The giant space telescopes, they'll be very sensitive, but we'll only be able to see at sort of a 10-minute arcsecond, so they can see Earths around sun-like stars. On the ground, you can build bigger telescopes, and because that inner working angle depends on the diameter of the telescope, on the ground, you can get in to very small angles. On the ground, you have the Earth's atmosphere above you, so you can't get very sensitive, but you don't have to if you're looking around these low-mass stars. So the ground-based telescopes, the 30-meter class extremely large telescopes, might be able to reach this habitable planet scale around the nearest stars, the M stars that we know are very common in the solar neighborhood. Well, the space telescopes would operate around the sun-like stars. So conclusions, these are all platitudes. We know a lot about the statistics of planets. We shouldn't believe we know a lot about their composition and nature, in my opinion. I should note, by the way, that Thursday's Kepler Astrophysics Colloquium will be by Caroline Morley, who's a brilliant exoplanet atmospheres theorist and knows a lot more than I do about the theory of planetary atmospheres and how to characterize them. So if you want all the stuff I've glossed over, you should come to her talk. But our understanding of planet properties is incomplete. Earth-sized planets are common, Earth-like. I don't know what any of those Kepler planets are, and I don't think we should say that we do know what they are. But we're moving into this era where we can characterize them with Tess and JWST, with direct imaging. Life-bearing planets, JWST will have to get lucky, but with these future either extremely large telescopes 10 years from now, or these giant space telescopes 20 years from now, we'll reach the point where we can see Earth-like planets. And I'll stop there, and again, sincerely apologize for taking long.
I just want to know is there any effect of these planets on the Earth?
Pardon me?
Is there any effect due to these planets on the Earth where we are living?
These planets are so far away they have no effect on the Earth. So the goal is just to study them, just to know if they're there.
One of those systems, not the one we saw. You said that there is an asteroid belt.
Yeah.
How do you know that?
So we know that from infrared emissions. So asteroids collide with each other, and that makes dust. Dust is really good at absorbing visible light and re-radiating it at infrared wavelengths. So we see excess infrared radiation from the star far beyond what the star and the planets account for. We infer the presence of dust from that.
So let's say it's an asteroid belt.
It's an asteroid belt-like thing. Dust particles don't stay around the star for very long. They experience Poynting-Robertson drag and spiral into the star, so they must be replenished. So there must be asteroids colliding all the time to keep them there. In fact, there's a huge amount. There's about 1,000 times as much dust in that system as in our solar system. So it's not just an asteroid belt. It's a very chaotic and massive asteroid belt.
Did I hear that these big guys that you can see in the image are 1,000 Kelvin
Yep.
and 20 million years old?
Yep.
Well, the universe is pretty old.
Yes.
So how many can you not see?
Right. So yeah. I didn't talk about our survey strategy much, but obviously what we do is we target stars that we know are young, and we believe we know they're young from stellar evolution models, though I have a postdoc in my group whose only job is to tell me that I'm wrong, that the stars are too old. Yeah, the galaxy has been forming stars for 10 billion years or so we can only see 1 in 100. We only bother looking at 1 out of every 100 stars for this survey, basically. But if we could fly the space telescopes, if we could get to that reflected light version, then you could see this around any star, and you could start surveying a large fraction of stars.
Any more questions?
One of the slides had a bullet about the effect of magnetic fields that you didn't mention.
Oh, astronomers hate talking about magnetic fields. One hand-wavy possibility for why the high-mass stars have bigger planets is that their disks would be more ionized, and so they could have different magnetic fields which would affect the migration of these millimeter-scale particles in them. But that's pretty hand-wavy right now. More like a crazy idea that came up at 3 in the morning when we're talking about how you get this distinction, and something that's actually supported by a model. But there is evidence that the magnetic fields could affect the migration of these millimeter-scale particles, and thereby have some effect on the planet formation process.
Okay. If no more questions, then do you think we